Good morning, good day, or good evening, depending on when you are watching this. My name is Lovisa Hagström, and I'm recording from Gothenburg in Sweden. For the Nonalida conference, I will present the paper Knowledge Distillation for Swedish Named Entity Recognition Models, a search for performance and efficiency. This work was performed together with Rickard Johansson at Chalmers University of Technology. It was made possible thanks to the Wallenberg AI Autonomous Systems and Software Program. Starting with the motivation for why we wanted to investigate knowledge distillation for more efficient natural language processing models. We have that we need more efficient natural language processing models. Since there are several problems with these increasingly power-hungry natural language processing models. We, for example, have that these models entail limited access to state-of-the-art models for natural language processing. For example, maybe not many of us can easily download and use a GPT-3 model. Also, we have that when we have access to the models, they are usually slow. For example, a BERT model is not that fast. Also, we have problems with that these models incur substantial environmental costs, for example, in terms of carbon dioxide emissions. So recently, several calls have been made for researchers to prioritize computationally efficient hardware and algorithms. While we all know that there is always a trade-off between model performance and computational cost, so what we wish to do is to reason about this in terms of model efficiency. And the way we try to reach better model efficiency is through knowledge distillation. So knowledge distillation is a model compression technique that can improve model deployment efficiency, and that is the efficiency of a model after it has been trained when you use it to make inferences, for example, in an application, which could be maybe of interest if you have an application that is frequently run where the model needs to make a lot of inferences. So the main idea behind knowledge distillation is to distill the knowledge from a larger model, which we denote as a teacher model. This model is usually better and has more knowledge, but it's heavier to run. And we distill its knowledge into a smaller model, which we refer to as a student model, which is usually worse in performance, but requires less amounts of computations to make inferences. So the student trained with knowledge distillation may attain a performance that is similar to that of the teacher, thus enabling us to potentially replace the teacher with a student at deployment, thus keeping the sort of performance the same, while we reduce the number of computations required in our application. Moreover, a student trained with knowledge distillation may outperform a model of the same architecture trained without knowledge distillation, such that we can replace them and see a strict increase in F1 score without any change in number of computations required at deployment. So with the motivation covered, we can take a look at the method and the outcome of our paper. So here in the method part, I will try to describe an overview of the choices we made when we evaluated knowledge distillation to try to get more efficient natural language processing models. So here you have an overview of the standard procedure for when we train a model without knowledge distillation. So here we have a model which I have named students. We also have our data, x and y. X could, for example, be a sequence of tokens. So what we do is that we give our x to the model, from which the model makes predictions, which we denote by ys. And then we base a loss on these predictions and on the gold standard labels y. Based on this loss, we can then do backpropagation to train our model. And this is the standard procedure. So when we do knowledge distillation, we add this teacher model, which is generally larger and heavier to run. And we also provide it with the x's to get predictions denoted by yt. And we include these predictions in our loss when we train our model through this loss term denoted by LKG, which is scaled by a hyperparameter lambda. So this is how we implemented knowledge distillation in our paper. There are different variations, but this is the one that we used. So to better understand this additional loss term for knowledge distillation, we can take a look at an example word. I picked the word Litauen, which in English means Lithuania, so it's a country. And you can see how the model trained without knowledge distillation predicts that this should be an organization or the first token in an organization name. And the model is actually correct because in this data set, the entities were given depending on how the named entity was used. So in this case, Litauen was actually referred to sort of more as an organization than a location. So we also, for example, have the predictions from the teacher model, which is generally better. And you can see how these predictions are a bit more smooth. And also that the teacher model thinks that there is at least some likelihood that Lithuania could be a location as well, while the teacher agrees that it should be an organization. So what we then wish to do is to make this student model approach the teacher in its predictions. And we do this through the knowledge distillation loss term, which we define to be the Kullback-Leibler divergence. So the more similar the predictions of the teacher and the student are, the lower this loss value will be. And you can here see how this results in that the student trained with knowledge distillation approaches the teacher in its predictions, and also seemingly its predictions are a bit more smooth. So with knowledge distillation explained, we can take a look at the downstream task that we chose to evaluate knowledge distillation and efficiency for. We chose the task of named entity recognition with data given by the Swedish SUC 3.0 corpus, and we pre-processed this corpus to agree with the standard named entity labels, which are usually used in named entity recognition datasets. And those are location, miscellaneous, organization, and person. Also, we measure computational efficiency for our models, since this is something we wish to evaluate knowledge distillation with respect to. So for each model, we measure the time required for one forward pass, the number of parameters in the model, the number of floating point operations required for training the model. That is for training the model from scratch until it has converged in evaluation score. And we measure the number of floating point operations required to make one forward pass in the model. So this is, for example, important when we wish to have a model that is quick when it makes its inferences, for example, in an application. And here you can see the models that we evaluated with and without knowledge distillation. So you also have some features of these models, number of model parameters, number of inference flops, and inference time. You can here see that we have a BERT model. This is a BERT-based uncased model, and we strictly use this one as the teacher model for our knowledge distillation. You can see here that it is, in every aspect, the heaviest model to run. We also have a window model, which is the simplest model to run, and this model is based on a sort of windowed approach when looking at contexts of words based on CNN layers. We also evaluate LSTM layers, LSTM models. So these models have one LSTM layer of different size. Additionally, we evaluate models with pre-trained embeddings. So we take the word embeddings from the BERT model, the teacher model, and infuse them into our models to see whether this improves model efficiency. We also evaluate deeper LCM models, so models with a depth of 2, and we also evaluate a dropout in one model. Finally, we also try out a char CNN word LCM model, which was a sort of state-of-the-art model for named entity recognition before the use of deep contextualized word embeddings. So with models described and the knowledge distillation approach described and our method for measuring model efficiency described, we can take a look at the outcome of our paper. Firstly, we have the results from training the models. So we have the number of floating point operations required for training, but also the F1 score of the model for held out test sets. And you can see here how the BERT model is the heaviest to train, and this was just for fine-tuning the model. I haven't included the floating point operations required for also training it from scratch, for pre-training it. We also have the simplest window model, which has the lowest F1 score while it's the fastest to train. And we have the LCM models, and you can see how they benefit with knowledge distillation, while it also generally means that the models need more floating point operations to train. And this was generally because these models needed more training steps when we trained them with knowledge distillation. We also have one maybe outlier, the deeper model with dropouts. It actually decreases in floating point operations required for training with knowledge distillation. We also have the char CNN word LSTM, the previous state-of-the-art model, which doesn't really differ in performance with knowledge distillation. We also have the results from deployments. So this is how many floating point operations were required for one forward pass have been measured for the models. And here it's important to have a low value here if you wish to use a model in an application where it might be used heavily. So you can here see how every model that benefits from knowledge distillation also strictly increases in F1 score without actually incurring additional computational costs. So this is a clear benefit with knowledge distillation at deployments. Finally, we can reach some conclusions. Those are that different models may differ in whether they benefit from knowledge distillation. We also have that knowledge distillation may provide us with models that are more efficient at deployment, while the computational cost of training a model with knowledge distillation generally is higher than without. And here, for example, I haven't even included the cost of developing the teacher model. But however, this computational cost might be worth it if you have a model where it's very important that it has a high deployment efficiency and where you know that it will be used frequently, such that it sort of catches up in the cost of developing it. Finally, we can take a look at some future work based on the results presented here. So for example, it would be interesting to create tools or metrics that better can guide us in this trade-off between model performance and computational cost. For example, what region is it good to be in with respect to F1 score and floating point operations required? Also, we can investigate different variations of knowledge distillation. There are several to explore. We may also investigate knowledge distillation for unsupervised training if we have small amounts of training data. And finally, why not also develop a Swedish distillbert? So with that, I would like to conclude my presentation and say thank you for listening.